Okay. Other particular questions want to look at?
There's another one on the same page.
Okay, that was spring 16, is that right? 15? Exam 3? Oh, which number?
Number 24.
24.
I don't know if we have to do that because we crossed something out.
No, you need to know how to find the power. Okay, no, yes, so you do need to know this. You need to know, first of all, that power is equal to 1 over the focal length. Yeah, this is 24 on spring 16. So you do need to know that the power is 1 over the focal length. And then you know some other things that you need to know. Let me just go ahead and write those while we're here. Is that
when it says diopters?
Right.
That's
So
the focal length?
no, that's the power.
Oh.
So the power, which is 2 diopters, is equal to 1 over the focal length. So then you have to find what is the focal length. And so it's 1 over 2,
Okay, that makes sense.
or 0.5. Okay? Don't forget, too, that the focal length, I don't remember if this comes up, but the focal length is half the center of curvature. That wasn't in that problem, but in other problems, it doesn't give you the focal length of the lens, but it gives you the center of curvature. And the focal length is always half that value. Remember with, like, say this is our concave mirror. Remember, the concave mirror is part of a bigger sphere. And so if I look at the center of curvature, it's in the middle, and then the focal length is right there. So the focal length is half the center of curvature, but it's also where parallel light rays will focus. Okay? All right. What other particular questions? Does that answer that one? Yeah. That is important.
So diopters is always
That's always the power. Any other particular questions? Yeah. What you got, Kevin?
Exam 4, spring 14.
Okay. Don't forget, know your parts of the eye and parts of the nerve cell. You're going to have those, of course. Okay, you have these same figures, same numbers even. Just know all the numbered parts, but then also know what they do, too. Because sometimes I ask the name of the object or the part, and then sometimes I ask what they do.
Okay, I have a question. She said hers is the same one as the last one.
Okay.
Exam 3, spring 17.
All right.
Number 23.
23.
This might be old. Yeah. Is it? That's old? That's old. Okay, that's from a different test. But I have something on that one.
Yeah, that was in the previous chapter on sound. Yeah. All right. What's that?
It was on that same test.
Okay.
29.
29. Two charges experience a force of 20 newtons, and then if I double the distance between the two charges, what is the new force on the charges? So F is equal to 20, right? And F, I know also, is KQQ over D squared, where D is the distance between them. And I ask, what if I double the distance between the two charges? So I'm doubling this. So that means that my force is 1/4 what it was before, because the distance is squared. And if I double it, that gives me a 4 in the denominator, 2 squared, right? F is squared. I'm doubling it. And so that means my force will be 1/4 its original value. And since it was originally 20, it's now going to be 5. You need to know how to do those. Those will definitely be on the test. Not just for that, but the other things that we looked at. And remember, you don't have to know the equation. I mean, you have to recognize the equations. They're on the equation sheet, so don't bother memorizing them. But you do need to know how to manipulate them in that way.
Number 45.
45? Same?
Yes.
Okay. So this is similar, but here I'm asking about the potential energy. And potential energy, if you look on your equation sheet, is not KQQ over R squared, but KQQ over R. Dang. Yeah, they all look very similar, right? Potential, potential energy, electric fields, and forces. I'll write those down just to have them all in one spot. Separated by 2 meters. If you move them to 4 meters apart, how much potential energy do they now have? First of all, are they going to have more or less? If I have these charges and I move them apart, are they going to have a greater inclination to move or a lesser inclination to move? Lesser, right, because there are less forces acting on them. And so whereas the energy was 8 joules, I know now that it has to be either 2 or 4 joules. So I had 8 joules here before. I double R. That means I get a factor of 2 over here. 8 divided by 2 is 4. Let me just remind you what those equations are. So we started with F is KQQ over R squared. And then we defined electric field, which is KQ over R squared. Now this is a force. This is a force per charge. So whereas this is measured in newtons, this is measured in newtons per coulomb. And then we moved on to potential. This is force, field, potential. V is KQ over R. So see, these are all very similar. They're all similar because they're all derived from Coulomb's law. And this is an energy per charge. And we need to know these basic definitions about what force fields and potential are. And then we had one last one. Potential is in joules per coulomb, R just volts. And then the last one is potential energy. Oh, by the way, with potential, look, it's joules per coulomb. That's an energy per charge. Fields are force per charge, so it's newtons per coulomb. So if you know the units, then you'll know the basic definitions of what those things are. N and C. Oh, so N is newtons. That's a measure of force. C is coulombs. That's a measure of charge.
So those are both like force per charge and newtons per field.
For what?
Per field. Those are both like ways that you can.
Oh yeah. So these are the units for the electric field. And then this is where we have these big ideas. This is sort of the definition of what the electric field is. It's a force per charge. But you can tell that from your units because this is a measure of force, this is a measure of charge.
Isn't volt U over Q like energy per charge?
Yeah. What did I write? K. Yeah. Yeah, I wrote that right here. It's energy over charge. Is that what you're asking?
Yeah, but it's just oh, that's the functional one, right?
These are the equations right here. Yes, I'm giving you lots of different columns. These are the units. These are the equations. These are on your equation sheet. These are like the definitions. And these are just, I don't know, the name of the thing. Oh, so then we had potential. Then we also had potential energy. Doing this last one, which is just an energy, just like we had in the work and energy chapter. And U is KQQ. I'm sorry, we're supposed to use D on all these, aren't we? You can put R if you want, but I'm going to go back and change these to D. Sorry about that. And that's just energy. Okay? If you wrote down R, it's not a radius, it's a distance between two charges or from the charge to a single point. Remember, too, that with these, well, you can tell this from the equation. I think there was a question on one of the tests about this. That some of these require that you have two charges, like two distinct charges, but then some of them you only need one charge. Which ones only require one charge? And? Right. You can tell from the equation, right? Only one charge here, but here I have two charges. To have a force, I have to have two charges. And here, to have potential energy, I have to have two charges. Because if you only have one charge, there's no force, and you don't have any force, then you don't have any potential for motion. That's a good summary of all that electric stuff, all those big ideas that we have floating around. And you're going to have to know the units. You're going to have to know the basic ideas of what forces, fields, potential, and potential energy all are. All right. I think y'all probably know this pretty well, but you want to review it before the test in the morning. Right? Okay. Okay. All right, what else?
50, 51, and 53.
Okay. These are good. Let me just pull up the equation sheet just so y'all are aware of what's there. Oh, this is not on your equation sheet. Yeah. We did talk about this, though, I'm pretty sure. That a 2 farad capacitor is in a circuit with a 10-volt battery. What charge is stored on the capacitor? Q is equal to C times V. You remember that?
I don't think we did.
Yeah, I don't remember it either. It's not on the test, if that helps you. But it just to tell you, it's 2 farads times 10 volts. Y'all don't care anymore, do you?
No.
All right, so it's 20 coulombs.
I mean, I knew that was the answer.
Yeah.
So I figured you had to multiply. I mean, that's the only.
Yeah, I don't remember doing that. I don't think we did that.
Never. It's not that.
Yeah. This, did we, yeah, we did the number 51, I think. Yeah. Okay. What was the other one?
51. Yeah, I did.
Okay. And 50 what?
53.
53. Okay, so those definitely are fair for the test. Okay, so 51, it's kind of like with the Coulomb's law. So I say not F, R is equal to rho L over A. That's on our equation sheet. Where is it? It's right here. R is rho L over A. And I need to know what these are, right? This is my resistivity. It's just a constant. Some materials have a higher resistivity than others. Wood has a big resistivity. Copper has a low resistivity. L is the length. A is the area. So here, I decrease the length of the wire to 1 meter. It was 4 meters, and then I go to 1 meter. So I'm multiplying the length by a factor of a fourth. So I have a quarter in my numerator. That means I'm going to have a quarter over here. So whatever the original resistance was, it's now going to be a fourth of that, or it's going to be 3 ohms. Does it? It's easy when you see it, but when you're all on your own, sometimes it can be kind of difficult. Yeah. And tomorrow, you're all on your own. You're all alone. It's just you.
I need to go through all the math problems just so I could just memorize what's going on.
Okay.
And, it just helps me.
That's fine. If that helps you, that's great. I would rather you understand what's going on.
We'll get there. We'll get there. Maybe in lab.
Okay. Oh yeah, y'all are gonna be in lab next semester.
We'll get there in lab. Just not right now. Baby steps.
It's gonna be different. Lab.
53. And then that's the last one.
Lab is going to be different. I told you that?
Yeah. Don't scare us before our final.
Okay, so V is equal to IR. I want to know what is the current through the resistor. This is Ohm's law. V is equal to IR. We really need to know what these things are. This is my V. Look, I can tell because the units are V as well. And so 24 is equal to I times 2 ohms. Those are my units for resistance. What times 2 is equal to 24? 12, right. 12 amps. All right. Those are all good questions. Any other particular questions? These are all great. All right, let's hear. I think it's good. If you have them, I'm sure everybody else has them too, right? You all have these too?
Spring 17, exam 4. It's number 6.
Okay. You could see something like this now. It's important that you understand with index of refraction that the law of refraction, that's that n1 sine theta 1 equal n2 sine theta 2, you're not going to have to use that to calculate things. But you do need to understand that the law of refraction, even though it describes how light bends, that primarily the law of refraction describes how light does what when it enters into a medium. It slows down. And that's why it bends. That light bends when it enters a medium because it slows down. And we did that with the whole wave fronts and, like, the tank driving. And so here it's asking how much does it slow down. So N is equal to, what is it, C divided by V. Where here, this is the speed of light. This is 3 times 10 to the 8th. That's on your equation sheet, I think. Yeah, it's right there. 3 times 10 to the 8th. And if you have to do this, I'll have the numbers really easy for you. First of all, you need to know that the light is always going to travel slower in the medium. So I'm moving into this plastic. That means that it's going to be slower than 3 times 10 to the 8th. So it can't be any of those. The answer has to be B. I don't even have to do the math. I can just see that all the others are faster than 3 times 10 to the 8th. And so that has to be the answer. So this is 3 times 10 to the 8th. I want to be sure. Divided by 2. I really just have to do this part, right? What's 3 over 2? Oh, it's 1.5. Yeah. Okay? It will never travel faster than that 3 times 10 to the 8th. And I'll never give you a scenario. Huh? In a vacuum, yeah, it travels faster. Or not faster, but the fastest. Right, if it's in a vacuum, it's gonna travel that. Right, because in a vacuum, N is equal to 1. And if N is equal to 1, C is equal to V. So in a vacuum, it's 3 times 10 to the 8th. But whenever I enter a medium, it's going to slow down. It necessarily slows down. It doesn't necessarily bend, but it will always slow down. All right? These are important. All this is important. All right, you had another here?
9.
Yeah. 7. Okay. Good question for several reasons. Then we'll go to 9, okay? I give you several variations of this, and you will have, 1 or 2 questions like this. Like, what does the light ray do? Or what do you, seeing what the light ray does, what can you tell about it? And so let's just answer this question first. I always like to draw my wavefronts. And that tells me when I do this, that side where I just drew the little dot, speeding up or slowing down? No, that's the best way to look at it.
But I get it. Like, I just know that. Like, I have to teach myself how to get it, so I can get it how you do it.
All right. It speeds up, right? Because in order to turn in that direction, the bottom part has to zoom around while the top part's still going slow. So this thing is going to like zoom around like this. So it goes faster in N2. Does that mean that N2 is bigger or smaller if it's going faster? Smaller, right? Because as N goes down, V goes up. So N is smaller. That means C is the right answer. That N1 has the bigger index of refraction. I could. Uh-huh.
The odd thing about it is N equals 1 in a vacuum, and it always slows down when it goes to a medium. And if the angle's bending away from the normal line, it's speeding up. So you know that N2 has to be bigger because it's going out and speeding up. Smaller. I'm sorry. I confused people.
Confusing people.
No. Yes, it is smaller.
Yeah.
It's hard to explain.
I
but
appreciate
get it.
that. Like, I understand. If that works for you, that's great. But I like to think about what the light is doing. But she's really awesome.
I just put numbers in, like, you kind of know that, like, if you're going from glass to air, it's going to speed up. So then I know, like, glass is whatever in, and then, like, air is whatever.
Okay.
Yeah,
All right.
that's how I think about it. But
Whatever
it's
y'all
hard
do.
to explain it.
That's okay. Whatever y'all do is fine if it works for you. A couple other things I could ask you too is, does it speed up or slow down? So here, is it going slow or fast? Right? So, well, we've already answered that. Here it's going slow, and here it's going fast. The other question I could give you is, let's say I give you an n equal 1.5, n equal 1.6, or vice versa. And I ask you, what direction does it bend, towards or away from the normal? Yeah, it's going to bend towards the normal, right? Because if I think about my ray fronts, it's slowing down right there, and this is speeding around in that direction, and so it's going to bend in that direction when it comes over here. Okay, so this was big N, small n. And if you want to memorize that, that's fine. I mean, there aren't that many combinations. It's really just those two combinations. And if you need to memorize it, that's fine. But I've never memorized it. I think it's easier to just think about it along the way. Think about your twin propeller boat, or your bulldozer,
That's how I think
or
about
your
it.
tank. Is that how you think about a twin propeller boat?
That's just how I grew up. So
With a twin propeller boat? Yeah, if you want to go right, you just make this side go faster, right?
So the second one you drew is towards the moon?
What's that?
The second one you drew is towards the moon?
Yeah, I don't use that language on the test, towards or away from the normal.
You're gonna want to know if it speeds up or slows down.
Yeah, I might ask you speeding up or slowing down, or I might also ask you to describe the magnitude of the angle. So let me remind you too, while we're here, that when I'm measuring the angle, that I'm measuring this angle, that's my incident angle, and this is my reflected angle. So in this case, theta r is smaller than theta I. All right. Look, y'all hang tight for just a sec. I'll be back in 30 seconds.
Wait,
So the first picture is N1 is back.
N1 is, so this is how I think of it. Right when I see this picture, I know what my N's are going to be. So N is 1.5 for N1, and N2 is 1.3. And I think of it as N1 is glass and N2 is air. So if you're going from glass to air, air is going to speed up.
Okay, so the sign, like the line, that's what y'all consider one, right?
All right. What's next, y'all? Is this good? We clear on this?
Yeah.
Those are important questions.
14 and 15.
On this same one?
Yes, when it goes to movement, it slows down. And when it slows down, the line goes toward the normal.
15, I just need like an explanation, but 14 is an equation.
Okay, number 14. Look, y'all, 14 is, the reason it's hard is it just has a lot of extra information. Right. It doesn't need this, you don't need this, although look, the focal length is half the center of curvature. If I want to know the power is just 1 over f. So it's 1 over 2, which is a half. That's really the only thing that's hard about 14.
Oh, because it gives you the focal point.
Right.
Hope you use that one.
You what? And then consider this lens with an object on the left, image on the right. If you move the object farther away, what will happen to the image?
I thought it was going to go
Hmm?
further. I thought it was going to go further away.
You would think that, right? Yeah, but no, it actually moves closer.
Yeah, that's so confusing.
Couple ways you can think about this. One way you just think about the equation, right? That I have 1 over f equals 1 over, this is probably the easiest way to think about it, over plus 1 over dO, that if I make this go up, then this must go down. We did that back in the class at some point, but we were talking about the eye. Yeah, the focal length changing. But you can also change the image or object distance. This is not like an eye, this is more like a camera, where I move it back and forth. Right, think about, no, that's not a good example. Never mind. Okay. Oh, it will move, when the object moves farther away, the image will move closer to the lens. Because when this goes up, this goes down. And so the image will move closer to the lens. DI gets smaller. And that's opposite what you would think, right? You would think if the object moves farther away, the image will move farther away. But let's see if I can do it.
They go together.
They go together, yeah. Like this. If the object moves closer, the image moves further away. Is that right?
Yeah.
Yeah. Mm-hmm. Yeah. All right.
So you said if the image moves farther away, the object will get closer. Or no?
I wouldn't ask it that way. But yeah, that's true. That if I move the image, would that make the object move? That would be kind of cool. But if that were true, but just from a mathematical standpoint, right? Like if I make DI go down, that means DO has to go up.
And this has just as many questions as the other test, right? Like it's the same, like it's normal.
How many
Yeah.
questions do we have?
I think there are 54, so that's good, right?
Yeah, we did. We were hoping it wasn't like 41 like this.
You like the longer test because you can miss more.
Yeah.
Mhm. All right, what else?
Exam 3, spring 16.
Which one?
28.
Okay, so this is similar to what we were looking at before. I'm starting with this K, Q, Q over D squared, and then I decrease the distance to half that original value. So it's a half, it's squared, that's become a fourth, but it's in the denominator, so it comes up over as 4F. And I can think about that because if I have two charges and I move them closer together, the force is going to go up. And then it's just a matter of by how much does the force go up. And since the distance is squared, I know that it's going to be square in the change in the distance. This is spring 16. All right, what else on this one? I think that if there are questions that you don't understand, the book is a good way for you to go back and refresh your memory about that. No, I think the book is pretty good. I mean, some people like it, some people don't, but I think it's pretty good. But the notes are also, that'll be a good place. No, I'm not going to take anything in the book that's not in the notes or that we didn't say in class. There will be nothing that's just in the book. I know there are a few things, but most of the stuff in the book we did talk about it, unless I told you explicitly. 45?
I don't know if you have to know that, but I didn't know how
I
we
just
would
send
know
over
that.
like the thought process behind it.
Yeah.
Yeah, you should, I mean,
How would we know that?
which of those puts out more energy?
Washing machine. I would think a wash. Yeah, I thought a washing machine. But
Really?
Yeah.
No, I mean, this question isn't on the test, but just for life, you should know that. The highest energy device in your house is a heater. Yeah. So the washing machine is about 500 watts or so. The desktop computer is just like 100 watts, maybe less. The clock radio is just, I don't know,
But a lot of
10 or
people got
20
that
watts.
wrong. You gave the test.
Probably
I
not.
don't
Probably
remember.
didn't respond.
But a bathroom heater or your hair dryer is like 1,000 watts. That's why when you turn your hair dryer on, that's why it always kicks off the circuit breaker.
It does, yeah.
Because it pulls so much electricity.
Okay, so 4 to 7. And that
Wait,
recently
wait,
when I
no,
got
no,
that, I
no.
remember the
46
form.
first. Oh, I need an explanation on
Okay, so what do resistors do?
that.
Limit the flow.
Right, they limit the flow of electricity. They limit the flow of current. So if my resistance goes up, my current, it's limiting it more, so the current decreases. Or I can think about it in this way. V is equal to IR. If R goes up, I goes down. Yeah, that's a good way to think about it. What was it, 47?
Yeah, we just went dealing on this, so I don't remember what the formula was.
Okay, it's Ohm's law. V is equal to IR. Look, I think it's written differently on your equation sheet. Just because, no, it's not. Look, it's right there. V is equal to IR.
Oh, I see.
So if V is equal to IR, that's 12 is equal to I times 3. What times 3 is equal to 12? 4. Don't say, oh man, that's a good, like if you get that one on the test, that means you get it right.
Yeah, it's not 4, but
Or something similar to it. Right?
Hmm?
You get that one right?
Mhm.
Right?
yeah.
50? Yeah, so it's about capacitance. So look over here. We got this whole business about capacitance. The C equals kappa epsilon naught A over D. So I'm going to write that here. Need to remember what these are, right? This is just a constant, so it doesn't even really matter. This is the dielectric. Remember, if I put something, a capacitor is 2 metal plates, and if I put something like a piece of paper, a piece of glass, or wax, or whatever in between the 2 plates, what does it do to the capacitance?
The area increases.
Increases.
Distance.
Right. So
It stores more charge in this more area. Like a certain.
So you're talking about just putting a piece
I'm talking about putting a piece of paper in between them.
Oh.
So if I put a dielectric between the 2 plates, I just hear increases. Increases. It's going to make it go up. Because I can think about it mathematically here. If K goes up, that means that C goes up. That's not what it was asking there. It was asking about the distance. This is the distance right here. This is the area. If the distance goes up, excuse me, by a factor of 2, that means I get a factor of 1/2 over here. So the capacitance is changed by a factor of 1/2.
Would you ask like a problem like that about the dielectric?
Yeah. Okay, so
I don't
we can think of, it's hard to think of why the dielectric increases the capacitance. That's just sort of hard.
I think that's surface area.
Yeah, that's not really why. It has to do with the energy between the 2 plates. But you can think about it mathematically. Like the area is easy to think about because the capacitor is like a bowl for charge, right? If I make the bowl bigger, I can get more popcorn in it. The distance, I think, is a little bit easy because if I separate the plates, then that sort of spreads out the energy more, and they just can't hold as many charges. But the capacitor, the dielectric is a little more complicated. But mathematically, if I add a dielectric, then this is going to go up. Oh, something that you don't know, or you do notice, we talked about it, but kappa is always bigger than 1. It's always 1 point something, or 2, or 3, or whatever. So the dielectric always increases the capacitance. It always increases the capacitance. Remember, it does 2 things. It keeps the 2 plates separated, but then it also increases the capacitance of the capacitor. All right? What else we got? These are good questions. All right, anyone else? I can just sort of stream through some of these.
I think that might be it, like, because a lot of them repeat.
Yeah, a lot of the equations repeat.
Yeah.
There's
Mhm.
one of each.
Make sure you know about the E meter and the N body 230 and those various.
Something else that's different on the test, like on the test, it says that the N body is resistant something, but it's current in our notes.
Oh,
Just want to make sure. Well, one of them's opposite.
okay. Let me just make clear. So the N body measures resistance. It sends a current, right.
I think my notes are wrong.
I'm sorry. Is everybody clear on that? The N body, the thing that you grab onto when you do your body analysis?
Your body that measures the resistance.
Right. It sends a current through your body.
That's why you get a different one to your orange.
Right. Because your different parts of your body have different resistances. So it measures the resistance.
This says the
Right.
body measures current as contraction.
Yeah, it measures the current in that like translates to the resistance.
Yeah, I'm sorry.
Okay, so this says measures resistance, so they both pretty much measure resistance.
Yeah.
Okay.
It measures the E meter and the N body are both very similar. They measure resistance.
Okay.
Sometimes I like to say things just to confuse you. And it's
Because I've been telling myself this is wrong. Okay, so they both measure resistance.
They both measure resistance. They use current. They send a current through you, but they use it to measure resistance. Okay.
Ask us anything on a negative image distance or a negative magnetization.
Yeah, I saw those, and I looked back in the notes, and I didn't see anything about that in the notes.
I didn't use it.
So no, nothing. In some of the questions, they ask about what does a negative image distance or a negative magnification mean, but we did not talk about that. It might be in your book. I'm pretty sure it is, but we didn't talk about it, so it won't be in.
Which one? So we will have it.
That's correct. Okay.
So, exam 4 spring 2016.
Yeah.
Number 6. If that said air instead of water, would it bend towards the normal?
Well, let's see. I don't really know. I just have to think about it. If this is air, I know it travels faster in the air. So when it gets here, what's it going to do? It's going to go like this. So that means it'll look like that.
So it'll bend away. They both.
Oh, yeah. So water is the same.
Air bends away.
Yeah, water would be the same.
What is air going into water and gets towards?
So if it's
Right.
so air and water.
Right. If it slows down, it bends towards the normal. If it speeds up in the new medium, it'll bend away from the normal. So the answer for air or water is both bends away from the normal. It'll bend more if it's air.
And if you ask us about the
Just
Magnitude.
the angle.
so the angle would get like if it swings up.
Yes.
What's the magnitude?
So if it bends towards the normal, the magnitude decreases, and then it
You might ask us.
the theta.
Oh, yeah. So
Theta, sorry.
if it bends away from the normal, like this angle right here is bigger than this angle. So here, theta r, which is our refracted angle, is bigger than theta I, which is our incident angle. All right? You guys good?
You don't have to.
Yeah, I'm going to ask that one. You'll have a couple of questions that have to do with index of refraction.
So if it's if the angle gets bigger.
Yes.
Theta gets bigger.
But don't try to memorize it. It gets a lot better if you just think about what happens to the wavefronts. What happens right here when that wavefront enters?
It goes fast.
It goes faster. And if it goes faster, while this side over here is slow, this side is going to be fast, so it's going to turn in that direction. Like a twin propeller boat. If you want to turn one direction, you make the other side go faster. Or a bulldozer. Or a tank.
A lawnmower?
Yeah, or a zero-turn lawnmower.
I'm going to South Louisiana. Literally from there. I don't know about the tellers.
She's from Texas, though, right?
Yeah, it's like.
They don't mow their grass in Texas.
Pasture.
Yeah. All right. What else, y'all? No, we didn't really talk much about the body part, but it's probably about equal parts, physics and body stuff. So make sure you know the body stuff. A lot of that's just identification, knowing the terms. Y'all good on that? Yeah. Yeah. Okay. Is that all y'all? Or you have more questions? What's that?
Exam 4, spring 14.
Okay. Exam 4:14.
25. I don't know why I can't understand this.
Yeah, it gets smaller for those who are wrong.
Spring 14. Yeah,
Which one?
25.
Okay. So remember we said there were two kinds of rays that you can draw. There's parallel to the axis and through the focal point. That's sort of definition of focal point, right? And then the opposite of that, which is through the focal point and parallel to the axis. So I have one here that's parallel to the axis and then through the focal point. That one's okay. And then I have one that's through the focal point and then parallel to the axis. That one's okay. But look, this one right here, not okay. That's B. So only two rays, parallel to the axis and through the focal point. That's what parallel rays do. They go through the focal point. And then the opposite, through the focal point, parallel to the axis. Those are the only two rays you have to consider. There are several others that we can draw too, but those are the two that we'll think about. All right. That might be something that's not in the book, but it is in the notes. So I think that's one of the few things not in the book.
What was the second one?
Parallel to the axis through the focal point. Through the focal point, parallel to the axis. They're just opposites of one another. See? Parallel through the focal point. This one goes through the focal point and parallel to the axis. All right, what else? Sure you know your parts of the eye. Know your parts of the nerve cell. Any other questions? No good? We're good? Nervous?
Yeah.
Don't be nervous.
I am nervous.
It's time to get it now.
It's hard.
Yeah, it's at 8 o'clock in the morning.
Yeah, I know. Can we move it back to
No, we cannot.